Calculus refers to a stone. But that doesn't mean that doing calculus has to be as hard as a rock. Hi, I'm Dr. Ron. Welcome to my channel. Whether you're starting high school calculus, university or college calculus, or taking it online, I'm here to help you not just get through it, but to do well in it. Let's get started. If you Google the word origin of calculus, you'll find it says, from Latin, calculus means pebble. It was a small stone used in counting in Roman times. Many of you will go on to careers in medicine, and you will hear the word calculus in reference to a small stone in the body. For example, renal calculus is a Latin term for kidney stone. What calculus does for us is it answers two very basic and seemingly unrelated questions. The first of this is, what is the rate of change in our mathematical model? In other words, what is the slope of this curve at any given point? The second question, again, seemingly unrelated, but as we shall see, is just the other side of the same coin, is what is the area underneath this curve? We get an answer to the first question using what's known as differential calculus. We'll concentrate on differential calculus first. The answer to the second question will come later under what's known as integral calculus. Let's take a closer look at differential calculus first. In order to understand differential calculus better, we need to go all the way back to Algebra 1 and geometry and review some of the concepts that we learned in those courses. And we'll see that calculus could be as straightforward as understanding some simple Algebra 1 and geometry. The first of those concepts that we'll address is the idea of the slope or rate of change. As you recall from your Algebra 1 courses, you were taught the equation y equals mx plus b, the equation of a line. The important part here for us is that m value, the slope, equal to the rise over the run, y2 minus y1 over x2 minus x1, which was sometimes written as delta y over delta x. We'll be using this concept quite a bit, this delta y over delta x idea. We can think of this as two subtractions, y2 minus y1 over x2 minus x1 over one division. That's what rate of change or slope is all about. The slope of our line can be positive as shown in the left-hand graph. This means that the value of y will increase as the value of x increases. We can also have a negative slope as shown in the middle graph, where the value of y decreases as the value of y increases. Finally, as shown in the right-hand graph, we can have a zero slope, where the slope doesn't change at all. In other words, the y value remains constant as the value of x increases. The second concept of interest in calculus is the idea of the secant line and the tangent line. The tangent line, as you will recall, is a line that touches a circle at one and only one point. The word tangent line comes from Latin tangere, meaning to touch. A secant line, one that touches a circle at 2 points, is one that cuts through the circle, from Latin secare, meaning to cut. We can put these two concepts together, that of a line with a slope and that of a tangent line, and apply it to a nonlinear system, such as this arbitrary curve. Arbitrary meaning I just drew it up. I'm going to use these toothpicks to represent potential tangent lines to my curve. There's one that might be there. Here's another one at this local maximum, and another one that's potentially descending. The issue here is that a tangent line touches a curve at one and only one point. This is a problem because I know I need a minimum of 2 points to draw a particular line with a particular slope. And so which one of these is the correct tangent line? I can move these toothpicks around a little bit here or there and ask, well, is that the tangent line? Is this? How do I know? How can I be exact? The trick with that is to use the concept of the secant line. Again, because a secant line has 2 points that it goes through, I can know for certain what the slope of the secant line is. Let's take a closer look at that with a simpler function. Here's a model of a function, a curve, made from some electrical wire, a bamboo skewer, and some twist ties. Imagine that what I'm interested in on this black electrical wire curve is the tangent line to the curve at point P. We're going to consider point P as to being our fixed point. Now, I can draw a line with another arbitrary or auxiliary point Q, which is a secant line, and I could know what its slope is exactly. That's algebra 1. Now imagine that I'm going to allow my point Q, or more specifically, the x-coordinate of point 2, x2, I'm going to allow that point to approach x1, the point of interest. Notice how the slope of my secant line, the bamboo skewer, is approaching the slope of the tangent line, that little red line that I drew. Do you see that? I'm letting x2 approach x1. How close can I allow x2 to approach x1? And the answer is, in my mind, as close as I want to. I could let the distance between x2 and x1 be less than, say, the diameter of a hydrogen atom. I could let that distance be less than the diameter of an electron. I can let that distance be as close, as small as I want to, as long as I still have 2 distinct points. I could still draw a line. Now we're going to imagine, what if I could let x2 be right on top of x1? Well, I can't, because now I'll be back to square one with 1 point. But the idea is this. I can see what that slope would be if I could allow x2 to be on top of x1. And that's the trick. That's how we get the slope of the tangent line to a point on any curve. Here's the same concept as illustrated on a board, the way your teacher or professor might show you. Again, I have a fixed point P and an auxiliary point Q, and Q can approach P on the curve. It's sliding down. And as point Q approaches point P, the slope of my secant line approaches that of this red tangent line, as shown with this ruler. Again, it's the same idea. It's the idea of what we call the limit. How does the limit work? In order to learn more about limits, hit that subscribe button, like this video, and click on this link to the next video on limits. I'll see you there.